All right, today we don't really have any new notes. We learned everything in yesterday's video, but we are going to go through example problems where we're going to solve for measurements of angles. So if you just want some examples, you can click through the video to the problems and work them for yourself, or you can work through them with me. We're going to start off by figuring what we can figure out if we know measure of angle 9 and measure of angle 5. And then we're going to name how we know the things that we know. So here, I want to kind of focus our view. So angle 9 is right here. And we know that W and V are our parallel lines, meaning that we don't know anything, because 9 is along line P, we don't know anything from number 9 about what's going on with line Q. So if I had this on a paper, I would put a pencil or my finger over it and just cover everything on line Q, because none of that is relevant to what's going on with these two parallel lines and the transversal of P. So angle 9 tells me all 8 of these angles because W and V are parallel. So I know that 9 is 80. Meaning that 11 is 80. The corresponding angle over here, number 1, is 80, and its vertical angle is 80. The others must be supplementary to that. So if this is 80, 10 is 100, 12 is 100, 2 is 100, and 4 is 100. So we know all 8 of those just by knowing measure of angle 9. So now I'm going to go the other way, and I would cover up line P, and we'll see what we can figure out about the other line. I'm going to do that in a different color. So for line Q, we know that measure of angle 5 is 68 degrees. So I know that 4 of these are going to be 68 because W and V are parallel and Q is a transversal, meaning that this angle is 68, this angle is 68, this angle is 68. The other 4 are going to be supplementary to 68. So 180 minus 68 is 112 degrees. And these are all in degrees, even though I didn't write a degree symbol. I should. So these are all that. All right, so let's talk about how we know the things we know, what the relationships are. So angle 12, we know is 100 degrees. And we know that relative to angle 9 because it is a linear pair with it. So we could call that a linear pair theorem, or just it's a linear pair. Angle 4, so we don't know anything between 4 and 9 because they don't have one of our named relationships. But now that we know angle 12, it and 4 are corresponding angles. So it's also 100 degrees, and that would be the corresponding angles postulate. Corresponding angles postulate. Number 7 is down here in the orange. Let's look at number 1 because it's still up here. So 9 and 1 are also corresponding, making it 80 degrees. So corresponding angle postulate. So I'd say this is corresponding to angle 12. This is corresponding to angle 9. 16, 3. So all the rest are in the orange. So let's move on to those. Angle 7, we started off with angle 5 right here. 5 and 7 are vertical angles. So we know that it's 68 degrees by the vertical angle theorem. And if we wanted to say vertical angle to angle 5. Number 3 was up there. Number 3, we knew 1, and those were vertical angles. So number 3 was 80 degrees, and it was vertical to angle 1. And then number 16 is down here. So now that we knew, what did we just found? 7. So 7 and 16 are supplementary, so we know that this is 112 degrees by the consecutive interior angle theorem. Consecutive interior angle to number 7. So that's what we're looking for when we talk about finding the measure and then giving the justification. So what relation to a known quantity did you have that let us justify it? What postulate or theorem let us do that? There's a second one of these for practice. So the only difference here is that both pairs of lines are parallel to each other. So P and Q are parallel, but M and N are also parallel. So if we know angle 3 is 102 degrees, I'm going to go back to my blue, so this is 102 degrees, then I know all 8 of these angles because M and N are parallel. But I also know all 8 of these angles because P and Q are parallel. So I could think of M as a transversal of them, or P as a transversal of these two, meaning that there's really only 2 total angle measurements going on here. So 1, 3, 9, 11, 13, 15, 5, and 7 are all 102 degrees. And I'm not going to go and write all of those, but actually let's just color code. So blue is going to be the 102s, and then orange will be our supplementary angles, which are going to be 78 degrees. All right, so now we have our measurements, and there's only 2 different ones here. So angle 5, we started knowing angle 1. No, we started knowing angle 3. Sorry, 3 and 5 are alternate interior angles. So angle 5 is going to be 102 degrees by alternate interior angle theorem. Number 11, as far as number 3 is concerned, is a corresponding angle. So again, if P and Q are the 2 parallel lines and M is the transversal, we're looking at these 2 intersections. 3 and 11 are corresponding. So that's corresponding angles postulate. Number 15, 11 and 15 are corresponding, so same reasoning. Those are both going to be 102. Angle 6 is a consecutive interior angle to angle 3 where we started. So this would be consecutive interior theorem. And it's going to be 78 degrees. Number 7 is 102 because it's blue and it's a corresponding angle to that one. And number 14, we knew number 6, 14 is also going to be 78 because it's corresponding with number 6. So we know all, 16 of these angles just by knowing one of them, since we have 2 pairs of parallel lines. All right, next we're going to look at solving some algebraic problems with unknown values based on these relationships. So in this problem, we have an x, a y, a z, and here a known value, like a constant. So the most important thing is this one right here. That gives us a starting place where we can kind of anchor ourselves. So I could start by knowing that these 2 are a linear pair. I could write 135 plus 7z plus 1 equals 180, and I could solve for z. Likewise, I could start with these 2 because they are corresponding. So I know that x minus 30 equals 135. Lastly, then, once I know that, I could say those 2 are a linear pair, or since these 2 are consecutive interior, I could add them up to make 180. And say 2y minus 15 plus 135 equals 180. So I end up with 3 completely independent equations here to solve for my 3 variables. I could end up in a situation where I have a system of equations that I have to solve, but here I'm able to separate all 3, so I have my z equation, my x equation, and my y equation that are all completely separate 1 variable equations. So I can then solve each of those for those values. I'm not going to do that here because the idea was to set up the equations and figure out a strategy, not to do the algebra to solve it. You can do that on your own if you would like. Next ones, we have some shapes, but importantly, these shapes include 2 parallel lines. So these parallel, or more. So the parallel lines allow us to make angle relationships as if we had a transversal situation. So to kind of visualize that, I'm going to extend I'm going to try to extend these lines a bit and draw them out to the left and right. So these parallel lines, I'm going to make them a little longer. And then this transversal, I'm going to make it a bit longer. And this transversal, I'm going to make a bit longer. So now we can see two parallel lines. And if we want to know something, we can figure out something along a single transversal. So the right side of this triangle, there's no angle measurements along it, so it actually is not doing anything for us in this problem. We can just ignore it and focus on this transversal here of these two parallel lines. So looking at them, I see these two are interior angles, and there's an x and a y. So I want to try to make a relationship that only includes one variable. So I have some x's here and some x's here, and the relationship between these two, since this is my transversal, I have two corresponding angles. This is the upper right corner of this intersection, and this is the upper right corner of that intersection. So I know that 5x minus 5 is going to be equal to 4x plus 10. If I solve that, I'm going to get x equals 15. And then if I plug that back in to either of these, I should get the same measurement. So 75 minus 5 is 70 degrees. And 60 plus 10 is 70 degrees. So what that lets me do, now that I've plugged it in, I can solve for y because it's supplementary to that. So I know this is 110 degrees, and that would let me write the equation 6y minus 4 equals 110. So 6y equals 114. That's 1 less than 20, so y is equal to 19. So we get our y and x that way, and we are using transversal rules even though these shapes don't necessarily look like transversals. So if you'd like to try the others, you can. I'm not going to fully solve the rest, but I will talk about our strategy for working through them. So here I have my two parallel lines. There's a top one and a bottom one. Now I have stuff going on the left and the right side. So I'm going to focus on the left first because I see this 90 is a number all by itself, meaning I can easily figure stuff out based on that. So we're ignoring the whole right half of the shape and just looking at these two intersections of the parallel lines and this transversal. I'll just name it L, cutting across them. So this is an interior angle, and this is another interior angle on the same side of the transversal, meaning they're consecutive interior, and they add up to 180. So I can solve for y by writing an equation, 3y plus 18 plus 90 is all equal to 180. So that's going to let me solve for my y variable. Now y doesn't appear anywhere over here, so that means that we're going to now ignore the left side and solve based on what's going on here. So we have a different transversal, I'll call this one M, cutting across those two parallel lines. Looking at these two, they are also consecutive interior angles. So I can add them, which would be 25x plus 30, and also set that equal to 180. And we could then solve for x doing that, and we would have y and x, they're completely independent in this case. All right, next one. We have two sets of parallel lines crossing each other. And we saw on the last slide that that means there are only two different angle measures in this entire picture. So we know that this one and this one are the same. So that has an x equaling a y. And we know this one and this one are the same. That has an x equaling a y. So instead of setting it up, we could write a system of equations. Let's go ahead and see what that would look like. So we would have 5x equals 5y plus 5. We could simplify that by taking out a GCF and just say x equals y plus 1. Our other equation would be 11x plus 4 equals 13y minus 5. So I could then pretty easily solve this by substitution because the top one is just x equals y plus 1. I could plug that in for x right here and then solve for y, plug that back into here to solve for x. But if we don't want to work with a system, this one allows us a different way to do it. We have this one and this one have only x's and their consecutive interior angles. So I could instead say 16x plus 4 equals 180 and solve for just x. And then over here, I could do 18y plus 0, because I have a 5 and a negative 5, equals 180. And that looks like y is 10, and then I could find x separately. So this works in multiple ways, whether you see it as a system or whether you see it as a strategy to solve one variable at a time, you should end up with the exact same results either way. All right, so next one we have our two parallel lines. And we have two different transversals, one going this way, and then one going diagonally this way. So let's see what we can do about this one. We've got x and y. If possible, we would like to relate the x's to the x's. So if I look at this diagonal transversal, it forms this and this as alternate interior, because they're both between the parallel lines, so they're interior, and then they are across the transversal. One is to the right of it, one is to the left of it. So that means those two are equal, and I could write 3x equals 5x minus 20 and solve for x. Then I look at my y's, and it's slightly different because this 2y is stuck between these two non-parallel lines, meaning that I can't make a relationship between it and the 4y directly. So there's several strategies I see we could use here. We could add all three of these angles to make 180 because they're a triangle. Or we could say, now that we know well, let's go ahead and find x in this case. So 2x equals 20, x equals 10. So I could plug that in and find this angle to be 30 degrees. Then I could make an equation with only y that adds these two together to be a consecutive interior angle with 4y. So basically we're removing this extra transversal line and looking at only this blue one, or this first one, to where this is an interior angle and this is the consecutive one. That would give us 4y plus 2y plus 30 equals 180. And if we did the triangle method, we should come up with something that's going to give us an equivalent result. So there's not always just one way to figure out these problems. That's why we're going to say explain your reasoning and talk about what are those relationships. Are we using consecutive interior? Are we using a triangle sum? Are we using alternate interior? What are these things? How do we know what they are? Next ones, we have just some more problem solving. These are very similar, so I'll just talk strategy here. We have this transversal on the right that has this x and this 106, so we know they add up to 180 because they're consecutive interior. We know that 106 and 2y are a linear pair, so they add up to 180. Then, since we know these are two pairs of parallel lines, we know this 106 goes here and here because those are corresponding and corresponding. So 4z plus 6 also equals 106, and we can solve for z that way. Over here we have two different transversals going on again, kind of like on the last slide. So we know a few things. We know that 2y and x are alternate interior to this diagonal line. So they're equal. 2y equals x. We know that z and x are consecutive interior, so they add up to 180. We also know that these three together form a linear triple, I guess. They're supplementary if you add all three together. So 3x plus 90 equals 180. So we could start with just x and solve for it, plug that back in, solve for y, plug it in and solve for z. So that's our strategy to get through it, is to use this straight line of three angles that together are supplementary to find x, use alternate interior to find y, use consecutive interior to find z, or linear pair. Once we know y, we could do a linear pair between y and z. This last set we're going to look at, or next to last, is kind of a complex idea where we have, there's a bunch of different strategies we could use to find this angle of this middle in the angle of two transversals. One thing we could do is extend the transversals, and then it would be similar to the problems we've been looking at, where we can then focus on one transversal at a time to find information. We might need to use the fact that we know these triangles are 180 degrees, or use an exterior angle theorem that we learned in like 6th or 7th grade. But there are other ways to do it. So another way, using a piece of information we don't know yet, but some of you may know, is we could close this off and make a pentagon. And these are both right angles, so they add up to 180. And a pentagon always adds up to 540 degrees. So we could use the sum of those 5 angles as 540, or the sum of these 3 as 360 to solve for x, because we know a linear pair here. But I think the intended solution here is, and all of those work, right? There's not just one right solution, is to draw another parallel line across the middle. So this line is also parallel to these two, meaning that here I have a corresponding angle to 50. So we have 50 degrees there. And then here, x, the other half of x, is a corresponding angle to this one that I'll label y. Well, since these are a linear pair, I know that this is 80 degrees. So I have my two halves of x are 50 degrees and 80 degrees, so x equals 130. So we can use that same strategy on all of these, I believe. We just need to find the two corresponding angles. So if I split this one down the middle, then 144 is not the one we want. We want this outside one. It turns out to be 36 degrees, so that's the bottom half of this V here. And then this one, 62, is vertical to this, so those are both 62, and that's corresponding to the top half of my angle, so x is going to be 98. And then this one, we can do the same process. So 138 supplementary to that would be 42 degrees. And then this 39 copies over to here because it's vertical. And then if we split it, we have 42 on top and 39 on bottom. So we get x equals 81 degrees. Actually just 81, I guess, because the degree symbol is already included there outside of the x. That's why I didn't include it on these three. So x is just a number, and then there's a degree symbol attached onto it that adds the degrees. All right, so we have one more problem, but this one I'm going to use as an example to talk about an in-class activity we're going to do for tomorrow, which is a challenge. There's an assignment for it on Canvas, so you can read the details here and look at that one. I'm using this problem as an example of a complex kind of problem because it includes quadratics. So there's going to be a need to use either factoring or quadratic formula to solve this. So we know these two are alternate interior, so y squared is equal to 8y minus 15. To solve this, we need everything on one side, so y squared minus 8y plus 15 equals 0. That allows us to solve this one. I would probably solve it by factoring because I can see that 8 is made as the sum of 5 and 3, which make 15. So I know this is y minus 3 times y minus 5 equals 0. So y could either be 3 or 5. Normally in geometry, when we solve a quadratic, we end up with one reasonable answer and one not reasonable answer. So one that gives us a negative size of something, a negative number of degrees, inches, anything like that, doesn't really work in the real world. But here if I plug in 3, this is either 9 degrees or 25 degrees, both totally reasonable. 25 looks more reasonable based on the picture, but remember, we can't know anything about angle sizes from a picture. We can't even know for sure that this is acute, even though it's drawn as acute. Plugging in the same numbers here, I should get the same values. So if I plug in 3, I get 24 minus 15. That's 9 again. If I plug in 5, I get 40 minus 15. That's 25 again. So there's really nothing to say which of those it is. Neither of those is negative. Both of them are reasonable. So then I would end up with either y equals 3 and x equals, so that would give us 9, and then these add to 180. So 171, or y is 5, and x is the supplement of 25, which is 155. So if this were your challenge problem and there were 2 valid answers, I would accept either of those as being correct. I wouldn't need anyone to come up with both of them. So that is an example of how a problem could be pretty challenging by bringing in harder algebra concepts. You could also make one, I think, where there's no way around it other than to solve with a system of equations. So if you want to incorporate things like quadratics and systems into your challenge problem, feel free to do so. Just remember that you have to solve it yourself. So, yeah. And this is the example from Canvas that I put on the assignment of that problem. You're going to put your name, or if you work with a partner or a group, put your names, and you can make more than one problem. So if you work with a group and want to make several problems, feel free. Just put them as separate submissions and put the names of whoever worked on them at the top, along with which period you're in, and then put your problem, and then separate from it so that I can cut this out and use it as the challenge. Below it, or either even in a separate picture, but I would just do it below on the same paper, show working it out and getting your solution to make sure that it can be solved. I'd rather you not include anything that's just really complicated decimals or fractions just for the sake of that being difficult. But feel free to include, like I said, quadratics and systems and things like that. You can even include more complex drawings, so things like these where there was a kind of strange relationship going on there, but it's still solvable. Feel free to include creative things like that. All right, that's all for today.